configuration and motion of the Earth, the Sun and the other planets in the solar system was debated for ages till Ptolemy, a Greek scientist, put forward his geocentric theory. His theory stated that the Earth is at the center of the universe and that the planets, stars and the Sun revolve around the Earth in circular orbits. Later, Copernicus, a Polish monk, put forward his heliocentric theory, which stated that Sun is at the center of the solar system and that all the planets, including the Earth, revolve around it in circular orbits. And then Johannes Kepler, building on the work by Tycho Brahe, formulated the three famous laws of planetary motion that have been named after him. They are the law of orbits, the law of areas, and the law of periods. The first law, the law of orbits, states that all the planets revolve in elliptical orbits with the Sun at one of the foci of the ellipse. Let us conduct an activity to better understand this. Fix a drawing sheet to a pin board. Select 2 points, F1 and F2 on the board and fix 2 pins at the points. Take a string of finite length and pass it through a small ring. Fix the 2 free ends of the string to the 2 pins located at F1 and F2. Pass a thin pencil through the small ring. Stretch the string taut at the tip of the pencil and draw a curve on the sheet by moving the pencil as shown. Take care that the string is taut while you draw the curve. The closed curve you observe is the ellipse. Points F1 and F2 are called the foci. The midpoint of AB, which is denoted as O, is the center of the ellipse. For any point P on the ellipse, the sum of the lengths PF1 and PF2 is constant. So, as per the first law, the Sun is at one of the foci of the ellipse and the planets rotate around it in elliptical orbits. Also note that sum of the lengths PF1 and PF2 is always constant. Kepler's second law of planetary motion is the law of areas. According to this law, the line joining the Sun and a planet sweeps equal areas in equal intervals of time. Consider a planet revolving around the Sun. Let P1 and P2 represent its position at the start and end of a 30-day duration. Let A1 represent the area swept during this period. Similarly, let P3 and P4 represent 2 positions of the Earth during its revolution for a 30-day duration, represented by A2. According to Kepler's second law of planetary motion, area A1 equals area A2. The concept of Kepler's second law can be understood by the fact that the angular momentum of the planet revolving in its orbit remains constant. This is because it is under the influence of a central force. The force of attraction pulls the planet towards the Sun, and the magnitude depends on the distance between them. For a body under the action of a central force, the angular momentum L, which is the product of mvr, remains constant. Here, r is the radius vector, v is the velocity vector, and m the mass of the body. If p is the linear momentum of the body, then L is equal to r into p. If delta t is the time in which the radius vector sweeps an area, delta A, then delta A is equal to half multiplied by r multiplied by v delta t. Thus, delta A by delta t is equal to half r multiplied by v. On simplification, we get delta A by delta t is equal to half L by m. As L is constant, delta A by delta t is also constant. Hence, for a given time interval, delta t and delta A remain constant, thus proving Kepler's second law. Kepler's third law of planetary motion is called the law of periods. According to this law, the square of the time period of a planet is directly proportional to the cube of the semi-major axis of its elliptical orbit. That is, t squared is proportional to r cubed, where t is the time taken by the planet for one rotation and r is the length of the semi-major axis of its elliptical orbit. Kepler's laws revolutionized the field of astronomy and have helped people understand the configuration and movement of planets better. Most of us are aware of Newton's conclusion on an apple falling from a tree and the subsequent discovery of gravitational force. He showed that the force responsible for the fall of that apple was the same as the force that held the moon in its orbit. This implies that the force of attraction between any two bodies applies to all the bodies in the universe. This force is referred to as gravitational force. The word gravity is derived from Latin meaning heavy. The moon revolving around the earth is under the action of centripetal force, which makes it follow a curved path. This centripetal force is provided by the gravitational force between the earth and the moon, similar to that of the force between moon and the earth. The magnitude of the gravitational force between any two objects varies with the distance between them, as well as their masses. According to Newton, the moon revolving around the earth has a centripetal force. which is due to the Earth's gravitational force. The centripetal acceleration of the Moon is given by the expression am equal to v square by rm, where v is the speed of the Moon in its orbit and rm is the distance between the Moon and the Earth. The velocity of the Moon in its orbit is derived from the fact that the Moon's orbit is circular of radius rm and its revolution period is t. Thus, the orbital velocity of Moon is equal to circumference of the orbit by its time period, which is equal to 2 pi rm divided by t. The expression on simplification gives us am equal to 4 pi square rm by t square. Substituting the values of rm and t in the expression and simplifying, the acceleration of the Moon obtained is much less than the acceleration of a freely falling body on the surface of the Earth. From this observation, Newton concluded that the magnitude of the Earth's gravitational force decreases with distance. Thus, based on the observations regarding forces, Newton proposed the universal law of gravitation. It states that every particle in the universe attracts other particle with a force that is directly proportional to the product of their masses and